embedded software and edge AI to clients across the globe. Matteo will show us how to adopt DevOps principle for FPGA projects, demonstrating how control automate HDR compilation and process using CI pipelines and introduce hardware into it.
Okay, thank you very much. Thank you for the introduction. So today I want to give you an introduction about DevOps applied to FPGA design verification. So I'm going to start talking about what DevOps is, why you should use it, and the tools that we can use for FPGA. At the end, I'm going to talk about how I apply DevOps when I was designing an ASIC for edge AI applications. We can skip this one. So what is DevOps? So if we get the definition from the software world, is a set of practices, tools, and cultural philosophies that bridge the gap between software development and operations. And the idea is to shorten the development cycle and to improve the quality of the software. Of course, it has a focus on automation, on collaboration, on quick feedback loop, and has processes like continuous integration, automated testing, infrastructure as a code. So I've been in this industry for about 20 years, the last 12 as a consultant. So I have the opportunity to talk about, with very different and lots of different clients. And so the thing I see are the issues I've encountered and see from customers is, for example, the release bitstream was built using a different source code tree from the one tagged for release. So imagine you tag the source code tree for release, then you check out the particular tag you build on your PC, and then before building the bitstream, you make a change. So actually, the bitstream you have released is not corresponding to the source code tree that you checked out. Another one is the classic, it works on or builds on my PC. So again, if you use individual developer's PC to build a bitstream, maybe the next time libraries have been updated, the OS has been updated, the tools have been updated. Just to give an example, I've had clients, and I did a project for them in 2018 using Vivado 2018.3. And recently, they contacted me and said, we'd like to add some new features. And it's very likely that due to the extended features, new features, I can still use Vivado 2018.3. So you may imagine that that doesn't work well with recent version of Ubuntu, for example. Another one, which is a classic, is the only engineers that can do a release in on holiday business or left the company. Again, if the release process is not automated, even if it's well documented, it's prone to error because we're humans. And also, it doesn't help to scale the team. So what works for a team of 1 FPGA engineers, maybe it doesn't work when you have 5 engineers or 15 engineers. And the last one is, it's not possible to replicate the environment or get the source code. They wish to build a particular version as a bug. So imagine after 5 years, a client, someone contacts you, there's a bug in a particular version. And the first thing is, well, try to replicate the bug. And then you want to get the source code that you used to build that particular version. And you say, well, it was 5 years ago. What about using the latest and greatest version? And the problem is there's no guarantee that the same bug is still in the latest and greatest version. It's just maybe there's a different way to trigger that particular bug. So let's start with version control. So you pick your favorite version control tool, Git, Perforce, CVS, and yes, SVN. You take the entire directory of the project, you commit it, job's done. Well, not so fast. So particularly in FPGA development, and I'm not singling out any particular vendors, you have hard-coded paths, absolute paths. There's a lot of codecs generated. So imagine you have your IP cores. So you have the definition IP cores, and then all the code generated as part of the IP generation. So you don't want to commit the code because it's pretty much guarantee you that at some point you're going to commit a version of the IP configuration that is different from the output that you are committing in the version control. So, and this applies also to bitstream too. So use git ignore or similar for your version control, and basically you just keep what you have as a source and not the output of the source. Which generally means you have to write your own scripts, some Tico scripts. In Vivado, you have project BD. Does a lot of legwork for you. Of course, you don't have to write your own script. You can use Hog, since we are here at CERN. There are presentations from previous FTF or on YouTube if you want to see how to use it. So what's next? Continuous integrations. So continuous integration is basically a tool that builds, tests, and runs any tools that you like. Every time you push a new version or as part of your merge request process, et cetera, or whenever you like, really. And the idea is to improve the code quality because you have a very quicker feedback loop and you kind of find issues as soon as possible. There are a few tools, of course, use whatever you like. There's GitHub, GitLab, Jenkins, etc. GitHub and GitLab have the advantage that there are complete tool suites. So it's not just CI, you have repos, you have issue management, you can store the artifacts of CI inside GitLab or GitHub. And also, all of them are actually distributed architecture. What this means is that the software that kind of kick off the build can be on different machine from the machine that actually does the build. And this is important because you might have different requirements for your build. So you might have a very powerful PC with lots of cores to build the FPGA, Yokt, etc. And then maybe you have another machine which is connected to your device in the test to do some hardware in the loop testing. And all of them support Docker to do the build. And what it means is Docker is a lightweight virtualization environment. And you describe the machine that is going to do the build through a text file. So basically, infrastructure as a code. And it actually means that you can save the Docker file in your version control. So again, we kind of answer one of the issues that I took earlier. So what you do, you build a Docker image that has all the tools you need. So you start from a particular version of Ubuntu, then you add all the packages you need, Vivado, simulation tools, libraries, etc. There are some vendors that provide their own Docker container, like Altera. I've seen recently they provide their own Docker tools. You can make your own. I have a few for Vivado, if you like, even one for ICE. And how the build is represented in the CI tools is a pipeline, which means you see different steps with dependencies, etc., that are needed to build a particular output, a particular artifact. So, for example, this is a dashboard from GitLab, and actually you see 3 steps. So the first step, actually this was a Vivado design with the IP from an external Git repository. So the first step is to check out all the submodules. The second step was doing running some simulation tests using CocoDB on this particular IP. And then the third step was to build the entire type-level design. And the nice thing is, once you've done this, the artifact will be saved in GitLab or GitHub, and then you can download directly the artifact from GitLab itself. Now, I said earlier that you might have a version of the FPGA bitstream has a bug, and you want to see, okay, what was that particular source code tree? So there are different ways to do this. At bare minimum, you can store the short Git hash inside the FPGA itself, so that is 32-bit number. You can save in some register. You can read from your system on chip, or you can save it as a JTAG user code, so you can read it from JTAG, for example. Regarding IP cores, I think there's probably some different opinion compared to Hog on this one. Technically speaking, you don't need that, because if your top-level repository will import external IPs, this will be, Git some modules or repo plus some manifest or something that already has everything that you need to get the correct source version of the IP. If you talk about software, Yocto or any kind of software, and again, you can store the Git hash. So for Yocto, you can store Git hash in U-boot as an extra version, with the kernel as an extra version, and for Yocto as OS version, so /the OS version, and you can add the Git hash. Then we probably want to also track the hardware itself. So imagine you have different version of the hardware, or you want to know a specific serial number of the particular board. So if your system chip has a serial number, of course, you can use that one. Or you can have on your board what's called a silicon ID. So it's a symbol chip. You can read, basically it has just 48 or 64-bit number. And the, in this case, analog devices guarantee that that is unique. So you can have it on your PCB, and you can read it from my controller of your FPGA. And if you want just to keep a track of different version of the board or different revisions, so you might want to have different revision A, B, C of the PCB, and you want to know which one the bitstream is mounted on, because you want to have a unique bitstream for all of them. You can just simply use some 0-ohm resistor on your PCB. And so if you go to the Starware Design GitHub, there's a simple block with the actual interface, and where you can store the Git hash, the 32-bit hash, and then you can have a few IOs that you can get on pins and set the board revision and the board type using some 0-ohm resistor. And also the advantage of the serial number or silicon ID is for RMA. So imagine you get the board back from a client, there's some issue. We can kind of keep a history of what happened to the particular board. Linting. So linting is basically a basic static code analysis that check for compliance against a set of rules. Generally speaking, you have two different types of set of rules. One is style. For example, use spaces, not tabs. And what can be defined more like good practices rules. For example, if you have a switch case statement, make sure you have a default case, for example. Of course, you can use existing rules, modify them, create new ones. And in terms of tools, I think the one I like more is Variable, and is open source project from the Chip Alliance. Of course, you can use Verilator, so I know it's a simulator, but it has the option to do just the linting, or you can use SVLint. And the nice thing about Variable is that support GitHub Actions. So what you do is you see the output of Variable as part of the web user interface and kind of embedded with the rest of the code. So actually, it's very easy to understand what was the problem that was flagged by the intro. Again, in terms of verification, you can install all the simulation tools, libraries, etc. in your Docker container. You can use your favorite framework, UVM, UVVM, CocoaDB, you name it. For CocoaDB, I generally use the runner, and then you can get directly the output in JUnit, XJUnit format. And this is basically an XML file, which has a list of how many tests were in total, how many tests were run, how many tests passed, how many tests failed, plus you can have output from the test, how long it took to run a particular test, etc. Unfortunately, there's not something similar for UVM or UVVM, as far as you know. So for UVM, you can write your own custom kind of UVM report server, and you can then generate the XML file. And for UVVM, I think, as far as I know, the best option is to just write a parser of the output when you generate the unit yourself. There's a library in Python to do that, so you can do that. And this is, again, another example from a GitLab dashboard. This was very simple, a single test with CocoaDB. Again, what you can see here is you get basically a dashboard of how many tests were run, how long it took to run the tests, et cetera, et cetera. And you can get metrics like, are you increasing the number of tests over time, et cetera, et cetera. So what about hardware in loop testing? So what does it mean first? So it means you have infrastructure around your device and the test where you can download and upload the firmware with the version that you build using CI. And then you have an infrastructure around it so you can inject some stimuli and get some result from the board itself. Lately, I've been playing with, there's a lot of options for this. Lately, I've been playing with LibGrid, which is basically a Python framework or library, which is maintained by Pengutronics. And what it does is abstracts the control of hardware, and specifically for embedded system running Linux. I think they've done some example with Zephyr, but specifically with the system running Linux. And since it's a Python library, you can write your test using PyTest, which plays nice with CI. So already from PyTest, you can get the output in JUnit, XUnit. It has support for very different type of hardware. So these two are actually two devices actually our own. This is what I picked the pictures. So the first one is called SDMax. So imagine you have your device, which boots from an SD card. So you have the bitstream, Yocto, et cetera, on your SD card. And what it does is you connect this board on one side, insert the device in the test. Then you have an SD card. Then you connect it to the PC, which is running LibGrid. And what it does is before starting the test, it can update the bitstream, the root file system, et cetera, without physically switching SD card. And the one that bought is simply a relay board with a Ethernet interface. But then they have a library for Visa instrumentation, et cetera, et cetera. The reason why I was playing with LibGrid is you can use your device in the test both as a part of the CI infrastructure, but also interactively. So imagine you have in your office a rack with all your products, board farm, and they're all part of your CI infrastructure, so you run tests every time you push new versions. But then there is an issue with a particular test. So instead of unplugging the board and taking it to your office, you can remove the board from the pool used by LibGrid, and then you can run your test directly. But I think could be interesting, even if I haven't used them lately, is to track metrics across different builds. So imagine you can keep track of your how many flip-flops he's using on your FPGA design, how many lookup tables, how much time margin you have, etc. And basically what you do, you plot each metric for each build. So imagine you see a sudden spike in either direction on FPGA usage, and then it's probably a good thing to try and understand why that happened if there's no good reason for. So for Jenkins, there's a good plugin called Plat. There's exactly that. So you parse, as a part of the CI pipeline, you can parse, for example, placing out results, timing results, etc. And you generate a CSV file. That CSV file has all the metrics that you like. And then, again, in the pipeline, you specify you want to parse this particular CSV file. And Jenkins will keep track and plot all the metrics across different builds. So this is not particularly exciting because it's all flat, but you get the point. As far as I know, there's no equivalent for GitLab with GitHub. So I think the only option is probably to push the metric from a GitLab CI pipeline to InfluxDB and make your own dashboard with Grafana, which I understand is not as easy as using the plot plugin. Okay, so last thing, I want to talk about a real-world example. This was a project that I did for a startup in California. And it was about audio AI ASIC. And so basically kind of ASIC that can detect a certain number of keywords or acoustic events like gas breaking, etc. And so the client decided they wanted to have an FPGA board where you can put the ASIC design in it and to do some testing to get it to potential customers, etc. So they had a FPGA RTX 7, has the microprocessor in Linux, SD card, etc. And the kind of test setup that we use was the same used for Amazon Alexa qualification. So if you want to qualify your device, you have the kind of Amazon Alexa sticker. That has a PC with 2 speakers. And one speaker does the keywords or utterances, and the other speaker does like a background noise. And basically what he had in that case was quite a few repositories. So there was one repository for the IP with their own QQTB testing. There was the FPGAs at top level. There was the Yoctolino image. There was the software running on the test board, the AI model, etc. So you can understand they're quite a complex pipeline. And in this case, I had multiple runners because there was one runner to build the FPGA. And then there was another runner which would run on the PC that you've seen. And we'll play the keywords, and we get back the results. And you can have a look if you want to know more. I have a playlist on YouTube with more details about what I've discussed today. Thank you.
Thank you for the nice talk. If you have any questions from the audience? I don't see. OK, we have Davide.
A very nice talk and nice methodology. So we try to follow more or less this pipeline that you show, this workflow, let's say, especially with OG, as you mentioned. One thing that, so here at CERN, we are mostly using GitLab. So you didn't explore much. I'm talking now from a project management view. If you have some suggestion how to integrate the GitLab workflow with the issues and everything in a good way with a project over like a complex.
That's a good question. And what I generally do, for example, of course, I'm a freelance consultant, so it kind of depends the kind of project I'll tackle. In general, I'll always start from, once I have a specification of a client, I will start creating issues in GitLab, which again is already a feature that you have. And then we'll start doing like a Kanban of tackle one feature at a time, create a branch, your feature branch starts working. And the fact that you have CI, every time you merge back to main, you have all the support for rebuilding the image, run the simulation, etc. And plus, you have all the kind of time management in GitLab when you have issues. So you can say, how long is going to, or you think is going to take? Are you tracking against what you think is going to take? So from a top-level project manager point of view, you also can keep track who's working on that particular features, how close you're to completion. Or, for example, you have a new release, you can simply tag all the issues, saying these need to be completed for the next release, and then until they are done, then you don't do a release, for example.
Great. Do we have any other questions? OK, so if not, I have kind of a question. It's more of a, let's say, discussion. So I always wanted to put hardware in the loop and do testing on hardware, but I was always hesitant to do that because in most of my system, I don't have simply an FPGA. I have an FPGA plus an ASIC that does stuff. Typically a front-end ASIC that gets data from a detector. And so I was wondering, in these cases, what's the best approach? Because okay, I can, for example, have in some cases the detector there gathering data, but they won't be the real data that I get normally. I can have an emulator, so like another device with another FPGA, but then I have to trust that that device is working correctly. So
yeah, sometimes. So, for example, I've also done some kind of ASIC development, and in those cases, what you will do, you'll put some test mode in your ASIC, or some sort of like a signal generator in your ASIC. So you actually do some testing on the board with your kind of detector ASIC, which generates some fake data.
okay, but this is if the ASIC was designed.
Of course, of course.
With that in mind. Okay, great.
I mean, also it kind of depends on the kind of signals that go into your detector. Is any signal generator you can get that kind of emulates, arbitrary waveform generator can generate those. I think that will be my suggestion. So it's something you can generate with the signal generator or arbitrary waveform generator. That will do. And for example, in LabGrid, they have support for Visa, so you can integrate all the instrumentation pretty much, from everyone can support Visa.
Okay. Yeah. Thank you for the suggestion. Okay. If we really don't have any question, let's thank our speaker and all our speakers for today. Great.